This chapter is about forward contract. The highlights of this chapter is first we're going to talk about the implicit or synthetic forward rates. Then we're going to define what a forward rate agreement is. We're going to compare forwards with futures to see the differences. And finally, we're going to be talking about the forward yield curves. So the definition of the forward rate starts with the following graph. Imagine that you have two interest rates. So you have the 0 1-year interest rate and the 0 coupon 2-year interest rate. And then what we want to find out is what is the rate that is going to happen between year 1 and year 2. It's going to be written as R1, 2. And this is called the forward rate. So forward in the sense that it doesn't start at t equals 0. It starts sometimes in the future. So in this case, it starts at t equals 1. Let's see an example of where can we find forward rates. So imagine that we have that the R1 rate is 25%, that the R2 rate is 20%, and that we have the following scenario. That in 1 year, I want to borrow $1,000, and then I need to return this $1,000 2 years from now. So in year 2, I'm going to return the $1,000 plus interest. And then I want to know how much do I have to return. So if I had the R1, 2, this would be very simple to compute. It would just be the $1,000 times 1 plus the R1, 2. Since I do not have it, let's see how we're going to proceed. So R1, 2 is not available, so we're going to construct it synthetically. So what I'm going to do is I'm going to take this $1,000 and then I'm going to discount it to times 0 at a rate of 25%. I'm just going to rewrite what's in here. So I'm going to take the 1,000, discount it at this rate, 1.25, and I'm going to get some value here. This value is actually going to be 800. And then once I have those 800 here, I'm going to bring them to the future at this rate, to this t equals 2. So once I bring this 800, so at t equals 2, I'm going to have 800 times 1.2 squared, and this is going to give me 1152. So here, what I'm going to be receiving is 1152. You asked at year 1 for $1,000, and you have to return 1152 in year 2. Then from this, you can imply what this R1, 2 is by using this equation here. So the 1,152 is equal to 1,000 times 1 plus R1, 2. And then you're going to get that the R1, 2 is 15.2%. So this is the way to construct your forward rate synthetic. Let's put some order into our formulas. So I took my 1,000, I discounted it times 0, and then I brought it into the future at this R2 rate, and this is equal to the 1,000, and this is how we would get the R1, 2 from this equation. In general, we can write, instead of 1 and 2s and so on, I'm going to write it in terms of S and T, where we assume that T is higher than S. So in our previous case, T was equal to 2 and S was equal to 1. And this would be the general formula. Now what's going to be different here is that in order to analyze your rate, you need to adjust it for the time period. You can also write it in terms of discount factors. So the discount factors is going to be the S, that means the lowest one is going to be on top, and the T, the highest one, is going to be at the bottom. Let's see another example of our forward rates. So imagine that Procter & Gamble is going to undertake a capital expansion. So they will need to borrow money for a 3-year period. Now, the loan, this is important, the money that they want to get is not going to begin until year 2. That means the year 0, 1, and 2, nothing is going to happen. And the amount of money that they want to borrow is $60 million. And today, the two things they can do is they can borrow money for 5 years at 15% per year, and they can buy or sell a 2-year bond in the market that pays 10% per year. So this is how the rates would look. Now, in here, they're going to receive the 60 million, and in year 5, 3 years later, 3 years after year 2, they have to pay back the 60 million plus interest. So now let's see how we can figure out how much they have to pay and what the forward rate is going to be. Now the forward rate is going to be the one that is going to go from year 2 to year 5. So the first thing is that they receive 60 million at t equals 2. So the question is, how much money do they have to lend at t equals 0 in order to get 60 million at t equals 2? So basically you're looking at the PV of 60 million discounted at the rate of 1.1% for 2 years, and this would be equal to 49 point. So this is the amount of money that they would need to borrow today. And the second question is now, where do they get the 49.6 million at t equals 0? So one of the things they can do is they can issue 49.6 million of 5-year bonds that will pay the 15% rate that is available in the market, the R5 rate. And then this means that at t equals 5, they will repay the 49.6 times the 1.15 to the power of 5. And this is equal to 99.8. This means that the effective interest rate on the 3-year loan from t equal 2 to t equal 5 is 60 times 1 plus R25 to the power of 3 equals 99.8. Hence, R2,5 is equal to 18.5%. Let's put that rate here. So this is going to be the R2,5 is 18.5%. We can also use the formula from the slides where we replace T and S, and then we're going to get the same 18.5%. So now we move from forward rates to forward contracts. So the forward contract is basically a contract that is signed at t equals 0. So it's something that you agree upon today for a loan that's going to happen in the future between time S and time t. So in our example, in the last example, it happened between S2 and t equals 5. And basically, the forward rate is going to be RST. In our previous example, this rate was R2,5. All terms, including the interest rate, are fixed at time 0. So this is important. Forward rate occurs at time 0, and then we fix everything at t equals 0. No money is going to change hands at time t equals 0. This means that at inception, the PV of a forward rate agreement is going to be equal to 0. So then the question is, how do you determine this RST? And then the way we did it was by deriving it in this form. So now let's think of that same example we did before with the forward, and to think about it as a forward rate agreement. So in this case, as we saw before, it's okay, they're going to lend me $1,000 at t equals 1. I know I'm going to repay 1152 at t equals 2. Now, what's the PV of the FRA? We already saw that this PV at inception is going to be 0. So you compute it as, so the 1,000 is going to have here a positive sign, and the 1152, since you're going to return it, is going to be with a negative sign. And then the PV of these two cash flows discounted is going to cancel out, and it's going to give me a PV of 0. The next question is, assume that immediately after you sign the contract, the interest rate change. So now this one is not 25 anymore, it's going to be 15, and R2 is not going to be 20%, it's going to be 10%. What is the PV of your FRA? You should pause the video here and do it yourself. So you go and apply exactly the same formula that you have here. So you take the 1,000 and you discount at a rate of 1.15, and then you subtract the 1152 over 1.1 squared, and you're going to get minus 82.5. So this would be the new PV, the new present value of your forward rate since the interest rates change. There's something very similar to forwards called futures. There's some differences between forwards and futures. Forwards are private contracts, while futures are standardized and traded on exchanges. So the future, you're going to find it in the Mexican Stock Exchange, for example, or in the Chicago Board of Exchange, and so on. Now, forwards, you would find them only between two private entities, like two banks. Scotiabank decides to trade with BBVA, for example. Now, in forwards, there's not a single cash flow exchanged until maturity or until the delivery date. With futures, it's different. Futures are mark to market, as the vocabulary used, daily. What does that mean? It means that every single day, because interest rates change, then whoever party is losing money on the forward rate agreement has to put that money into an account. Basically, they have to maintain a margin account, and then in the margin account, they put the value that they lost. So the 82.5 in the previous case, whoever party is on that side is going to have to put that money, and this money is going to go to the counterparty. Now, Why do they do that? The reason to do that is so that the risk of losing money is reduced. Like if every day you ask your party, hey, like you're losing money today, hence the other person is making money, please put that money down, and you're avoiding that one day they come and say, you know what, I don't have any more money. Now, this is one of the risks that you can face in forwards, which is that the party comes at maturity and says, listen, I don't have the money, like this is too much and I cannot cover it. Forwards and futures are different in that one is mark to market daily, the other one is not. In general, futures and forward prices are slightly different because futures have less default risk because of this margin requirement thing. Now, this daily settlement is going to make the present value of the position to change constantly, and it would limit the losses in case of default. Now we're going to think about what a forward yield curve would mean. So we already saw what a zero coupon curve is, and now we're going to think, okay, what does a forward yield curve mean? So a forward yield curve is basically the same thing that the zero coupon curve, but it's something that is a rate that it's going to start in the future. So for example, let's say it starts in 1 year, S, and then it can go from S to S plus 1. So it would be R1, 2, but since it's a curve, you can have as well R1, 3, R1, 5, and so on. It contains the same information as the spot yield curve, because the only thing that we're doing is we're using that formula that we derived before, that it depends on our discount factor, which are the ones gotten from the zero coupon curve. So it has exactly the same information. Now, the important thing is it might provide some valuable information. For example, here we have at every single day, so let's say this one, in 1991, we have the implied forward rate. So it would be this. So that day, the zero coupon rates were telling me, okay, this is what's going to happen with the forward rates starting that day. Now, you see that the 3-month LIBOR, so these are a bunch of 3-month rates implied by the zero coupon curve. You see that in the future, this is what happened. So actually, the red curve totally overpredicted what was going to happen. And then in general, you see that over this period, 1989 to 2009, the forward yield curve of the 3-month US LIBOR overpredicts what's going to happen in the market. Now, there's periods like this one where it underpredicts what's going to happen. But in general, it overpredicts. Another example, so here we have some zero coupon rates from R1 up to R9, and then the forward rates that start at time 1 and go up to from 2 to 9 are on the right hand side. Now, how do you get these ones? You get it from the formula below, and this is left as an exercise. So you should pause the video here and do it by yourself. And this concludes the chapter on forward rates.